In this video, I want to continue on with the introductory materials and information that you're going to need pretty much the entire time you go through this course. And one of the things that you're going to be doing a lot is you're going to be doing unit conversions. In unit conversions, you're going to be changing your units from one type of unit to another. In everyday life, you've probably gone from yards to feet. The unit conversion to go from 1 foot to 1 yard is you multiply your number of feet times 3 and you get a yard. That's a unit conversion. And in these, we're going to be mostly converting things into SI units. And there may be other units. Maybe you might need to convert something into English units. So I want to demonstrate how to do that. If you'll recall, in the first video, I found the area of the piece of paper. That area was right around 600 centimeters squared. Okay, I want to demonstrate how to change the units into inches squared, and I'll demonstrate how to change it into square meters as well. Okay, so whenever you do a unit conversion, what you're essentially doing is multiplying whatever value you've got by the number 1. But it's not just any old one. It's a very careful choice of the number 1. And basically, the amount on the top is going to be equal to the amount on the bottom. So if we go from square centimeters to square inches, what we're going to do is, if you look up in the inside cover of your textbook, you'll find the unit conversions for many things. And you'll see that there's 2.54 centimeters per 1 inch. Okay, this is an example of the number 1 because 2.54 centimeters is the same length as 1 inch. That's how unit conversions work. That's how you find your choice of the number 1. So if we go 600 centimeters squared, and then we multiply, we say 1 inch. The reason you put the inch on the top is because the square centimeters here, this is roughly over 1, right? Needs to be able to cancel out with the square centimeters in the bottom in order to have that work. So 1 inch is 2.54 centimeters. And if you look at that, the centimeters, here's a centimeter squared, there's a centimeter, only one of those would cancel. And it's a little bit tricky when you've got a squared term or a cubed term or something like that. This conversion needs to be squared or cubed if you've got a volume that you're talking about, okay? So this whole entire thing needs to be squared. So then when you multiply it through, this will be square centimeters. It will cancel with the square centimeters on top here, and you'll end up with square inches. And so if you run that through, 600 divided by 2.54 squared, okay, you square the 2.54 as well as the unit. 2.54 squared centimeters squared. And when you run the numbers, you should get 93.0 inches squared. And the reason I added the 0.0 is because this was that 3 sig fig number, okay? If you can go back on the first video if you don't remember why on earth it's 3 sig figs, and it will spell out how we came to that conclusion. And we want our value at the end to match that, because here's 3 sig figs. Actually, 2.54 centimeters is defined to be 1 inch. So this isn't just 3 centimeters. This is not just 3 sig figs. It is exactly 1 inch. So it's a definition, just by the way. Here's how you do a unit conversion. If we wanted to take that 600 square centimeters and convert it into square meters, we'll go through that same process. 600 centimeters squared. And then our unit conversion in that case, again, we want the centimeters on the bottom. There are 100 centimeters in 1 meter. So this is our choice of 1. Okay. These are the same lengths. Again, because this is centimeters squared, we need to square the top and the bottom to get everything into the correct units. So we'll square this whole entire thing. Okay. And so then you'd have 100 squared centimeters squared. 100 squared, that's 10 to the 4th, just by the way. Okay. And so then when you go ahead and divide that out, you'll get 0.0600 meters squared. Again, we include those 2 zeros there so that we have a 3 sig fig answer, the same thing as we started with. This right here is an accurate definition. There are exactly 100 centimeters in a meter. It's not 1 sig fig or something like that. This is a definition. By definition, there are 100 centimeters in a meter. And so that's how unit conversions work. And if it happens to be a quantity where you need to maybe multiply a couple more things to get the unit conversions, you can just multiply by however many things of one that you're talking about. The way you're going to figure out what value goes on top and what value goes on the bottom is you're going to analyze the units. All right. There's a thing called dimensional analysis that I'll spend just a little bit more time on. And you'll look at the units and say, oh, centimeters squared here needs to cancel with centimeters squared there. So inches goes on top because you want to end up with inches. You don't want to end up with 1/inches. Okay. And so that's how you're going to do unit conversions. And again, in this class, you will do them over and over and over again. And I'll go through unit conversions probably a number of times as we go through different videos covering different topics. Another thing that is mentioned in chapter 1 of the Giancoli text is estimating. And you've probably been all at various different get-togethers where somebody will have a jar of jelly beans or whatever it happens to be, and everyone will guess how many jelly beans are in the jar, and whoever guesses the closest gets the jar of jelly beans. And so that's one way of estimating. I am personally really bad at it. I virtually never win those things. But the idea is you can look at that, you can see how many jelly beans are on the bottom of the jar and estimate about how many layers deep they are, and then come up with hopefully a halfway accurate estimate. I don't know exactly how bad I'm at because I never kept the number that I guessed versus what the answer ends up being. So maybe I'm semi-close, but somebody else is always closer, which is probably just as well for my health. But that's one way of estimating. Another way of estimating is triangulation. And there's a really interesting example in the book where by using triangulation actually is how they estimated the original, like the size of the earth back in the days of ancient Greece. And they essentially, if you know the distance right here, then maybe you could find this little distance here, and then the radius of the earth is right here. And there are a couple of examples, I believe, at least one example in the textbook. And there are also some homework problems that I assigned because it's such a cool thing to be able to do. The example that I'm going to give you is not an example out of the book. It's one a few years ago. I had talked about predictions being made by good hypotheses. Einstein also predicted the existence of something called gravity waves. And on the strength of his prediction, a couple of observatories were built. One of them is actually fairly close to us. It's down in Hanford, and it's called LIGO. And then there's also a LIGO in Louisiana. And these are observatories, not like a normal observatory that looks toward the sky, but they've got these 4-kilometer long arms. And a gravity wave hitting these arms would cause one of them to compress and expand just ever so slightly. Again, 4 kilometers. And the expansion is smaller than the subatomic particles that make up the nucleus of an atom by several thousand times. I mean, they're infinitesimally small. And so detecting these things, as you might imagine, is really problematic because they're so tiny. And so they built these observatories, and they had to have these perfectly straight, level arms. And because they had to be perfectly level, the arms essentially go like this, so that one end would be resting on the ground. And by the time you end up 4 kilometers out, the other end is a certain distance above the earth. And a couple of years ago, they actually discovered gravity waves. They detected them, and which of course is super exciting in the world of physics anyway when a discovery like that is made. And it was particularly exciting for us because our department had just taken a field trip down to LIGO. I was like, ooh, we were there. We saw, this place where, physics headlines were made not very long later. Anyway, and one of my colleagues gave a talk on gravity waves. And he said at the far end of the 4-kilometer long run, the tube has to be approximately this far above the ground. And so I was teaching think a physics 100 or 115 class at the time. And one of the students came up to me and said, my friend is really good at math, and he said that my colleague was wrong on how far above the ground he has to be. They said, oh, really? Let's go ahead and run these numbers. Because I don't think so. My colleague is super, super smart. He would not, in a public speech, have messed up something as simple as that. I'm going to redraw my picture here just to make it a little more accurate. So I said, okay, let's run the numbers and figure out how far above the ground that the far end of this tube has to be. So here's a triangle. These are the radii of the Earth. Okay. The radius of the Earth is 6,380 kilometers. Okay. This arm right here is 4 kilometers. The question, here's a right angle, is what's this distance right here? This is the distance above the ground that was in question. And so we can simply write the Pythagorean theorem right here. We can say the radius of the Earth squared, that's one leg of our triangle, plus the 4 kilometers squared, the other leg of the triangle, equals our hypotenuse of the triangle squared, RE, plus, we'll call this little bitty distance here D squared. Okay. We can go ahead and multiply this out, and we can find out radius of the Earth squared plus 2 radius of the Earth times our D, because we'd end up with 2 of those terms when you multiply that out, as you should hopefully recall from algebra, plus D squared. Is this multiplied out? You can look at this and you can see that there's a radius of the Earth on both sides, and so we can subtract that from both sides and that will go away. And then so that we can get this into the quadratic format and be able to use the quadratic equation, we move the 4 squared to the other side. So we have 0 equals, I'm going to rearrange this, say D squared plus 2 of our radius of the Earth times our distance minus our 4 squared. I'll just say minus 16. Okay, so I move that to the other side. This equation is now ready to crank through the quadratic equation. And so if you will remember, hopefully, usually don't worry, I give you the quadratic equation on a test so that you don't necessarily get the opportunity to freeze up and say, now what was the quadratic equation again? But anyway, this is our squared term. The value that comes out in front is our A. The value that goes with that term to the first power is our B. And then the value of the term to the second, or to the 0th power, is the C as it goes through the quadratic equation. So I'm going to go ahead and write that over here. So we have minus B plus or minus B squared minus 4AC over 2A is our quadratic equation, as you may recall. And at this point, it's simply a matter of not messing up the numbers as you push them into the calculator. So minus B is going to be minus 2 times that radius of the Earth, minus 2 RE, okay, plus or minus the square root of 2 times our radius of the Earth squared, minus 4, our A term is 1, our C term is minus 16, over 2A. 2 times 1 is simply 2. Okay, and so I'll put a box around this to kind of separate it out from this other equation right here. When you run that through the quadratic equation, the only number that makes any sense is 0.00125 kilometers. Okay, and if we go ahead and switch that into meters, that's 1.25, or roughly 1.3 meters, which is indeed about this high, just like my colleague said. And so I spelled this out for my student, and I said, why don't you write this down and take it to your friend? So that is it's a fun activity. There's a couple of homeworks that I've assigned that give you an opportunity to try this. I don't think you'll be finding the D value, but you might be finding this value or something like that. Everything will be given except for one of those quantities. And so you'll sit there and you'll use the Pythagorean theorem exactly like I just did and solve for whatever unknown you happen to be looking for. So hopefully it will be as fun for you to try that as it was for me. Okay, the last thing that I want to talk about as we look at introductory material for this class is dimensional analysis. And dimensional analysis is kind of a little bit near and dear to my heart because it's a way that when I was taking physics back in the day, sometimes I wouldn't necessarily remember in a test situation what the formula was for a given quantity. But I knew what units it was supposed to end up with. And so I would look at the units of the quantities that I was given and say, now what do I have to do with these units, with these numbers, so that I will get the units of the answer that I'm looking for, okay? And so a very simple way to do it, dimensional analysis, is if we looked at finding velocity, okay? You may recall from maybe some high school classes, velocity equals distance over time. Okay, how far did you go divided by how long did it take you to get there. Okay, actually instead of velocity I'm going to call it speed. Okay, speed equals distance over time, and so distance has units of length. Time, we just say it has units of time, just like that. And so speed has units of length over time, all right? Or we could say meters per second. And so if you were in a test setting and you said, let's see, does speed equal distance times time or distance over time? Okay, imagine you couldn't remember that. Well, say you were given a distance that that thing traveled, and you were given how long it took it to get there, and you could analyze and say, okay, speed has units of distance per time, miles per hour, distance divided by time. And so which one of these formulas would give you that, that unit? So if we looked at distance times time, you'd say that would be, let's see, that would be length times time. And so if you were looking at it in English units, you'd say miles times hours. And it's like, nope, that doesn't make any sense. I've never heard of units that do that. Okay, that's not right. How about distance over time? You say length over time. In our everyday English units that we use, that would be miles per hour. And you could say, you know what, this is it. This is how I'm going to calculate that speed that I am looking for. And you would be right. Okay. The one thing that dimensional analysis does not do is it doesn't tell you if there's a half or a 2 or some sort of just a numerical multiplier. But many times equations don't have that. All you've got to do is analyze those units, crank things through, and you can get the right answer. And it's just wonderful and terrific and a nice way of getting to what you need to go. So if you have any questions on any of this, certainly send me an email and contact me, and I will help you work through it. So have fun with the course.